Great, so now we can have a bonus idea of how we can re-examine example 3 in terms of voltage and energy. So in number 3, we had an electric field, we had a mass of an object on a frictionless surface, we had a charge for that object, and we had a distance that it traveled, right? Well, now we know that the change in voltage, voltage is a scalar, change in the voltage is equal to the electric dotted with the distance. Well, that means we've got 7 times 10 to the 6th on 3 meters, so we've got 21 times 10 to the 6th volts. So we've got a change in volts of 21 times 10 to the 6th. Well, if we want to know what the work done is, we know change in volts is equal to the work over the charge involved. So the charge involved times that change in voltage, well, our charge involved is 10 to the negative 5th. The change in voltage is a whopping 21 times 10 to the 6th volts. And so that's going to get us 210 joules. So we've got 210 joules of work is done in that charge moving those 3 meters. Well, if we've got 210 joules of work put into the system, then since we started off at rest, we know that our kinetic energy is going to be 1/2 mv squared. We don't have to worry about there being any beforehand, so all of our energy went into moving the object on that frictionless surface. So we know that those 200 joules went into the kinetic energy equals 1/2 mv squared. We start solving it out. We've got that 2 times 210 divided by our mass of 35 kilograms. We take the square root is going to equal the velocity we've got. We punch that all out through our calculator and we get the exact same velocity we did before, 3.46 meters per second. So two very different ways to figure it out, but that's because we can connect the movement through our electric field to the change in the electric potential. That's a really cool idea, and that's got a lot of power for us. All right. Hope that made sense, and it'll be great to see you for current, because that's where things really get cooking. All right, we'll see you at Educator.com later.